Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a logarithmic equation with complex numbers, maybe imaginary numbers and all that stuff. Now if you're new to complex numbers, go ahead and check out my lecture videos and always ask questions because that's how you learn and improve. And if you like algebra, number theory, and trigonometry problems, then go ahead and check out my other channel, Cyber Math, the very first channel that I started a while ago. I think it's been more than 4 years, maybe, something like that. Anyway, Cyber with an S. So let's get started. I'll be presenting two methods, and one of the methods will use an interesting formula, which you may or may not know. I didn't know that. Okay, so let's start with the first method. So for my first method, I'll be doing what's obvious. What is obvious? We have an ln equation. So what would you do if you had ln x equals 3? I mean, you would consider the base e and just use the definition. Or you would just do e to the power both sides, right? I mean, that makes sense, doesn't it? Oops, did I write e to the power ln? I meant 3. Okay. And e to the power ln x, as you know, is just x, right? Obviously, if you're looking for real solutions, x should be positive, but complex, we don't care. X equals e to the power 3. That will be a single solution. But with the case of complex world, complex numbers, things are very different. We have multi-valued functions, multi-valued logarithms, so on and so forth. A lot of complications, a lot of complexifications too. So this is base e. Write a little e in there, just sneak it in there. And now we're going to use the definition. E to the power that equals the argument. So, in other words, this gives us z minus I over z plus I equals e to the power I pi over 2. Now, even though I said that complex numbers can be sometimes multi-valued because of the argument, you know, the rotations, the unit circle, the Argand plane, and all that stuff. Think about the angle theta, right? We usually start in the first quadrant, but doesn't matter. You can add 2 pi to it, it'll bring you to the exact same point. So if this is z, z is unchanged. But trigonometric representation, the polar representation, will look different. That's why, that's what we mean by multi-valued. But in the case of this, like what is e to the power I pi over 2, that should be a single number, right? I mean, that represents a single complex number. And that is, guess what? I. What? But you're like, why is it I? Easy. The reason is simple. Because Euler said many years ago that e to the I theta is cosine theta plus I sine theta. And this just represents a complex number with angle theta and modulus 1 in the complex plane or the Argand plane. This is real, this is imaginary, so on and so forth. And this is our number, e to the I theta. See? Its x component or real part is cosine theta, and the imaginary part is sine theta. And we just write it this way. Make sense? And this is called the standard form. You can write it as a plus bi, so on and so forth. But what's really significant is that when the angle is pi over 2, then you get a special number, which is imaginary. And that's our imaginary unit, actually. Because if you think about the imaginary axis, and in the positive direction, like upward, right? You have the I as our unit, and you can just multiply it by that, like a vector, right? Double it, triple it, multiply by even I. But if you multiply by I, that's going to become real. That's the thing, because multiplication by I is equivalent to a rotation. Make sense? Cool. All right, now, so this is I. Okay, now we got a much simpler equation, right? Forget about all the natural log and all that crazy stuff. Let's just solve for z. Easy, right? So let's do it. Cross multiply z minus I equals zi plus I squared. One thing that you should never ever forget. I squared is -1. That's one thing that you should never forget. You can forget everything else about complex number. I mean, obviously don't forget that. But if you do, never ever forget I squared equals -1. Hopefully I'll remember this too when I am like 95 years old. Who knows, maybe 100, right? Okay, so what do we do next? Z minus I equals Zi minus 1. Let's go ahead and solve for Z. To do that, let's put Z on a positive side. Or, I mean, everything else needs to be positive. Does it have to be positive? I don't know. we'll probably do this. Let's bring the I over here, zi over here, z minus ci, and add the I on the right-hand side because this looks fine. And then we're going to go ahead and factor out a z here, 1 minus I, and then this will be I minus 1. And then we're going to divide 1 minus I both sides. But notice that 1 minus I can never be 0 because I cannot be 1. By the way, I squared is negative 1, but does that mean I is 1? No. Does I equal negative 1? No. I is the square root of negative 1. Uh-oh, that's not a real number, obviously, because this channel is all about complex numbers. And I say the square root because it is the principal square root. I know that there are 2 square roots. For each complex number, there are 2 square roots, right? Except for 0, of course. 0 is exceptional, okay? So what is this equal to? Uh-oh, can we multiply by 1 plus I and get the answer? Like multiply by conjugates? Probably. Let's do it. I times 1, I times I squared, and then negative 1 minus I. I squared is negative 1. I cancels out. This becomes negative 1. And at the bottom, we get 1 plus 1, which is 2. That gives us negative 2 divided by 2 equals negative 1. Come on, you don't need to do that. Look at this. 1 minus I and I minus 1 are opposites. In other words, I minus 1 is negative 1 times 1 minus I, isn't it? So 1 minus I cancel out, and we end up with z equals negative 1. Are you serious? Z is negative 1 in this equation? Yes, it is. Now, let's look at it from another angle, which is called the second method. If I did not forget to include the solution from Wolfram Alpha, I'll show you that. And if I don't forget that, okay? I'm very forgetful, by the way. You probably noticed. Now, the second method relies on a formula, which I didn't know about. But this is how it works. I'm not going to prove the formula, but maybe in another video, we can do the proof, right? Hopefully. So here's how the formula works. We have 1 over 2i multiplied by ln z minus I. Pay attention to this because you're going to see something familiar. Z minus I divided by z plus I is equal to tan inverse of z. There's a constant, but I'm going to ignore that. I don't think it's going to apply in this case. I could be wrong, and correct me if I'm wrong, but that's what I'm thinking at this point. Now, what am I going to do with this? Well, I'm given that this part is I pi over 2. So just replace it with that. This is 1 over 2i times I pi over 2. And that's equal to tan inverse of z. Great. Let's go ahead and simplify this a little bit, shall we? This is I and I. I'm going to go ahead and multiply, and that's going to give me pi over 4. But let's just switch sides so we can get a nicer expression. Tan inverse of z is equal to pi over 4. Now, what is that supposed to mean? I could probably tan both sides, can't I? Let's move this a little bit that way. Uh-oh. Yes. Now we can apply the good old tangent on both sides, and we can get the answer, right? What is tangent pi over 4? Well, it's tangent 45, so it should be 1, right? These cancel out, by the way. We end up with z equals 1. Uh-oh, that was not accepted or expected. That wasn't expected, right? Why did it become 1? Isn't it supposed to be negative 1? So we probably made a mistake somewhere. Maybe there's a minus sign that I forgot about. I don't know. Anyways, unfortunately, this brings us to the end of this video. So that's for you to find out why this is happening. Well, thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.